right, the mole. What is a counting unit? Well, the mole happens to be one of these counting units. It's a numerical grouping. Can anybody give me other examples of counting units? Anyone? No, a counting unit. That would be for length. We would be measuring length with meters.
Counting units?
Yes, like for instance, how do you count? When you buy eggs, how many do you normally buy? A dozen. What is a dozen normally? 12. That's a counting unit. And that would be what, 14? Baker's dozen? 13, something like that? I don't know. Here are some other examples. See if you know any of them.
Dozen. Pair to ream.
How much is a ream? Anybody know how much a ream is? How much is a ream? Anyone? I happen to copy a lot, so I have to get reams of paper all the time.
Oh, is that 100?
It would be 500.
I should have known that.
How about a gross? Does anybody know what a gross is? Counting unit? It's a weird one, and pencils come in this number. I don't know why.
23.
144.
4 score.
4 scores, and how many years ago in the Gettysburg Address?
20 years. Wait.
This is a score with
87.
How much is a score worth?
20.
20 years.
20. There you go.
80.
So, counting units. All right, from the mole song, as you saw, having moles of something like even penny or paper or marshmallow size is not great for us because it pretty much wipes out the planet because it takes up way too much space. You can't get sunlight in and all that other good stuff. So, from the mole song, as you can see, the quantity is very, very, very large. Just how big is a mole, though? Let's try to give it some kind of idea. Soft drink cans cover the Earth to a depth of over 200 miles. If we stacked 6.02 times 10 to the 23rd soda cans everywhere. How about popcorn kernels? Those would go about 9 miles high, and those are really small in comparison. And last but not least, if you were trying to count them at even 10 million per second, guess what? It still would take you 2 billion years to count. Very large, humongous number we're talking about, but because atoms and molecules are so small, they can fit in a little vial like this 1 mole of water, as you saw from my little vial of water here. Okay? Now, what is a mole? It's 6.02 times 10 to the 23rd of anything. So you could have a dozen cookies and have 12 of them, but you could also have a mole of cookies. And then, of course, the Earth would be amassed with cookies and we'd all die again, once again, not being able to eat all of them and get rid of them. So, based off of carbon-12, measuring 12 grams of carbon-12 is where this numerical count was calculated from, 6.02 times 10 to the 23rd. And yes, although Avogadro didn't directly calculate this number, they attached his name to this number because he did do a lot of calculations with gases and moles in there. So Avogadro's number is 6.02 times 10 to the 23rd. So when you say a mole of anything, you could have a mole of shoes, you could have a mole of calculators, you could have a mole of pencils. But of course that would be ridiculous because really the mole should apply to being used for things that are really, really, really small, since it is such a large number. All right, now we're going to be looking at the way we represent the particles. Representative particles. There are 4 different labels you might see in order to use Avogadro's number. For instance, 1 mole of carbon would be 6.02 times 10 to the 23rd atoms of carbon. This is because carbon is an element off the periodic table. So anything that you see that is just a single element, you would label it atoms. It gets that label of atoms. 1 mole of water is going to be 6.02 times 10 to the 23rd water molecules, because this one happens to be a covalent compound. Covalent compounds we call molecules. Now you're welcome to abbreviate MLCS, because it's a long word and I know that's a lot to write. So when you're doing your T-charts and writing in your units there, you're welcome to do that since it's so long. Now referring to NaCl. NaCl happens to be an ionic compound, has a metal and a nonmetal, so we use the designation formula unit for it. So this is for ionic compounds. Anything ionic will have this label of formula units. And then if for some reason you dissociate your ionic compound into its ions, where you have the two separate ions here, and you see the charge on it, you see the charge on the symbol, then you would label it an ion. So there's 4 designations under the representative particle part of the mole map. It's always 6.02 times 10 to the 23rd of that particle is going to be equal to 1 mole on that part of the mole map. But you need to make sure that you're using the correct designation and labeling them correctly based off of what type of matter you have. Do you have an element? Do you have a covalent compound? Do you have an ionic compound, or are they ions? So if you see any of these 4 words, the conversion factor is going to be using Avogadro's number to equal 1 mole. Now, molar mass, you have previously done. Remember, you just multiply the mass off the periodic table by the number of atoms in each compound, and then you add them together to get the entire total. And then if you want to do percent composition, you can look at the particular element out of the entire element times 100. But here, when we're doing mole conversions, we're interested in the molar mass, which would be the mass of the entire compound, because that's going to equal that number in grams will be equivalent to 1 mole of the substance. So I'm just going to do a couple quick examples to make sure that you understand what I'm talking about, although you did complete the worksheet just the other day. So for NaCl, what you would do is you would look it up on the periodic table. Na, there's one of them in here, is 22.99, and we're rounding all of our masses on the periodic table to 2 decimal places to that hundredths place value, so we all get the same. Okay, and then the chlorine is going to be 1 times 35.45 off of the periodic table. And yes, I have a few of them memorized because I do this quite often. And you'll get some of them memorized because you'll be using like oxygen a lot, you'll be using hydrogen a lot, so you'll have some of them memorized, but some of them you'll have to look up. You add these 2 together. That looks like a time, so let's add it together. And you would end up getting 58.44 grams. And that equals 1 mole of NaCl. Okay? If I'm doing the iron 2 hydroxide here, I would look up iron, which I believe happens to be 55.85. The oxygens, though, now I have to distribute my 2, so don't forget to multiply that one by 2, and they're 16 each. And then you distribute the 2 to the hydrogen as well. Okay, so this ends up being 55.85, 32.00, and 2.02. And if we add this up, I believe it's 97.87 grams. That's going to equal 1 mole of our iron 2 hydroxide. You have to add up the masses. Each compound, each element is going to have a different mass, but it's going to equal 1 mole of that particular substance. One other last thing here is molar volume. Molar volume has to do with the amount of liters of gas in 1 mole at standard temperature pressure. And standard temperature pressure is one we use a lot in chemistry. STP for abbreviation. It's always 0 degrees Celsius in 1 atmosphere. 0 degrees Celsius, the reference point is what? What are we kind of referencing there to use that particular value? What is 0 degrees Celsius to you? Freezing point or melting point of water, right? Freezing or melting point of water. But does anybody know the reference point of 1 atmosphere? Where are they getting that pressure value from? It is the atmospheric pressure of the Earth, but where? At sea level. Very good. So the reference point is our atmospheric pressure at sea level. As you go up in the mountains in Colorado, there's going to be a lot less air up there, so the air pressure would be less. So we're referencing at sea level, 0 degrees Celsius. This is going to be the same value all the time. The molar volume is always going to be 22.4 liters. That's going to equal 1 mole of any gas at standard temperature pressure. And you'll see the questions will be phrased that way. It'll say at standard temperature pressure, what is the, how many moles of this gas do I have if I have this many liters? So you'll see them referenced that way. And yes, later on when we get to gas laws, I will show you how that 22.4 number was derived. But for right now, all we need to know that 1 mole equals 22.4 liters of any gas at standard temperature pressure. So far, so good? All right. Now here's your lovely mole map, and I suggest that you refer to it. It does give you the conversion factors. Do not forget your representative particles are going to be atoms, molecules, formula units, or ions. These guys all fall under this category. Molar mass, of course, is grams. And you look on the periodic table for these values. Go to the periodic table. And then, of course, volume of gas is 22.4 liters equals 1 mole. And you can see the different conversion factors. We're still going to use the T-chart method and fence method in order to show our conversions. But refer to your mole map, and everything always equals 1 mole in the middle for our conversions. Any questions on that? So far, so good. Because now we're going to look at doing some practice problems together. All right, so we're going to be starting with the sheet that says conversion, practice, and examples. I believe it's on the back of your mole map. So check that out there. Aluminum is often used for the structure of lightweight bicycle frames. How many grams of aluminum are in 3 moles of aluminum? So we start by putting out our T-chart. Create your T-chart. What goes in the upper left corner? That given information, what do they give us here? 3 moles of aluminum. So we put our 3.00 mole, and yes, the abbreviation is MOL. I'm sorry, that's just the way it is. Aluminum, you must put unit substance in there. So we put our given information in the upper left corner. Good. Now what do we do with that given information in the upper left corner? What do we do with this part of it at least? We diagonal it down. It goes down here, right? What are we wanting to know? We want to know grams. So where are we going to put that? On the top here. Grams of aluminum. Now everything equals 1 mole, so I put a 1 next to the mole. How do I figure out the grams? What do I refer to? The periodic table. So everybody look on the periodic table. How many grams of aluminum are in 1 mole? Round to 2 place values. 26.98, good. Now what do we do in our T-chart? We multiply the top, we divide by the bottom, and we end up with what is our calculator value? 80.94, but guess what? 80.94 is not the correct answer. We have to go back to significant figures. How many do we have over here? Remember, you start from the left. If you have a decimal, first non-zero, everything after that counts. So there's 3 in that value. So we start here, 1, 2, 3. Do we round up the 9 or leave it at 9? Leave it at 9, so this is 80.9 grams of aluminum. And you circle that. Do know that the moles are going to cancel like so. So what are we left with? Just the grams of aluminum. Pretty easy. These are the ones that I call other one-step conversions. You only have to do 1 step in them. We're going to do some 2 steps today. Later on, we'll get into ones that get to be 3 and 4 in length. But right now, we'll start with the basic and move on. Next. All right. Yes. This startling part of the PowerPoint to make you nice and aware of the next question. All right. Artificial sweetener aspartame. Here is the formula. It's a doozy of a formula. That also happens to be a nice organic compound, as you see. Has lots of carbon in it. Used to sweeten diet foods, coffee, and soft drinks. How many moles of aspartame are present in 225 grams of aspartame? So, let's start with our T-chart. What goes in the upper left corner, which is 225 grams, good. And because, like I said before, we're going to shortcut things, I'm just going to put asp. You want to write out this entire formula, you have fun with that. Okay, but you do need to identify the unit and the substance. So now we take this and we do what with it? Diagonal it down, grams of aspartame going to what? We're going to moles of aspartame, and so 1 mole of aspartame. This is where the fun part ensues. What do we need? We need the molar mass, so guess what we need to do? Let's get calculating. See, there's 14 of them. What is the molar mass of carbon? 12.01. And then we have hydrogen. There's 18 of them. What's the molar mass of hydrogen? And next, nitrogen. So we have 2 of them at 14.01, and last but not least, our oxygen, 5 of them at 16. So multiply all those, add it up, and tell me what you get. So yes, we would want to multiply and add up so all of our answer comes out to 2 decimal places. Anybody got it yet? 294.34 is correct. There's our grams per 1 mole, so we're going to put that down here on the bottom. 294.34. Now in this case, we're going to multiply the top by the 1, mentally of course, then divide, do your division, by the 294.34. What do we get there? What is your answer? And you give me the calculator answer, then we'll round it. 0.764, what else? 4. All right, that's good enough, because how many sig figs do we have over here? Only 3, so we need to keep 3. So remember that first 0 doesn't count. 1, 2, 3. Do we round up the 4 or leave it a 4? Leave it a 4. Good. And so this would be moles of aspartame. And do you remember the grams would cancel with the grams? Another one-step conversion here. But yes, when they have a huge formula, then the molar mass becomes kind of tedious to calculate, just so you know. Like so. All right, looking at the next one. Atoms and molecules in grams. What word is missing from this particular question? Moles is missing, so guess what? This one's going to take how many steps? 2 steps, because now we have to go to the mole first and then continue on from the mole to the other unit. And so here we're starting with grams and we're going to go to atoms. All right? So start your T-chart. Let's go with that. We have 35.4 grams of copper. And then I do what with that? I'm going to take that and put it down here. Grams of copper going to 1 mole of copper. I have to make a pit stop at the mole before I can move on to the second part. So looking at my periodic table, what is the number of, what's the molar mass of the copper?
63.55.
It is 63.55. Very good. But I'm not done because I don't want moles of copper. I want to continue on and find the atoms of copper. So now I'm going to take these moles of copper and do what with them? Put it down here. So moles of copper, 1 mole. How many atoms does that equal? The Avogadro's number, good. 6.02 times 10 to the 23rd atoms. Copper. Now the thing that you need to be careful with, especially on these calculators, is making sure you're using your exponent key correctly. Remember, you just type in 6.02, you hit the exponent key, and then type in 23 for the power. So you do not get that out of whack. If you type in a 10, then it will make it go up a full 10 power than it should. So don't do that. We multiply the top. Basically, what you need to do is multiply 35.4 times 6.02. Hit the exponent key, type in the 23. Then hit equals. Next is divided by, hit the divide sign, and then put the 63.55 in there. Hit equals and you should get your answer. What do we end up with for our answer?
3.35
Copper atoms.
It's usually unit then substance, but yes, copper atoms, here we go. And we would keep 3 significant figures as the person that said the answer rounded already, because there's 3 significant figures to start with. So this one would take 2 steps. Notice the cancellations, grams of copper with grams of copper, and moles of copper with moles of copper, leaving the atoms of copper behind. And that's what we got in the end. Any questions? So back here, let's check our answer. I'll do this one. Most of you set it up correctly. 78.4 grams of potassium. Yes, you would take your grams of potassium, put it down here. That's going to 1 mole of potassium. If you look on the periodic table, you should have gotten 39.10 grams if you rounded. Then, of course, we're not done because we want atoms, so we have to go 1 more step. So we take our moles of K, put it down here, and 1 mole equals 6.02 times 10 to the 23rd atoms. Okay, of K. And therefore, once you multiply and divide, what did you get for your answer? Anyone? 1.21 times 10 to the 24th atoms of K. Very good. 3 sig figs, because over here we round our answer to, because we started with 3 significant figures. Looking at the next one. What is the mass in grams of 1.20 times 10 to the 24th molecules of glucose? So this one's a fun one because it's lengthy in the fact that you have to calculate the molar mass. And we're going in reverse here. We're starting with the molecules and going to the grams. Same concept though. Set it up like so. And yes, like before, you can abbreviate the molecules here. And C6H12O6. Now I'm going to diagonal that down, take my molecules, put them down here. And that number would be 6.02 times 10 to the 23rd. That equals 1 mole of glucose. And then, because we don't want moles, we have to keep going. So we take the 1 mole of glucose, we diagonal it down here. And we go to grams of glucose. Then you have to do the molar mass. Another fun one that's a little bit longer than normal molar masses, but carbon, 6 atoms at 12.01 each. Hydrogen, 12 atoms at 1.01 each. And then oxygen, there's 6 of them, 16 each. When you do all that and add it up, what do you get? Anybody done it yet? Yes, no? Yes, 180.18 is correct. Very good. So then we can put that number up here in our T-chart, and we can now multiply and divide. So multiply the top, divide by your Avogadro's number. Molecules cancel with molecules. Moles cancel with moles, and then we're left with our grams over here of our glucose. What do we get for our gram value? Yes, 359 grams of glucose. We do have 3 significant figures to begin with, so we're going to keep 3 in our answer. Correct. Very, very good. Now the next one's a little tricky. Just going to tell you up front. How many atoms of O are present in 78.1 grams of oxygen? What's the trick here? Anybody know? Yes, oxygen is not O. Oxygen is O2. Okay, so we have to start out with working from the idea that we are dealing with O2. It's diatomic, don't forget. So over here, we're going to put the 78.1 grams. 78.1 grams of O2. Now, take those grams, diagonal them down just like you would normally, and go to the mole. Okay. How many grams of O2 are there in 1 mole? This one's an easy one. You can mentally do it. 2 times 16 gives you 32 grams. Very good. Now we continue on. What do we have to go to before we can get to the atoms of O? Moles can go to what, though? What is O2? Is it an atom, a molecule, a formula unit, or an ion? Is it an atom, a molecule, a formula unit, or ion? It is a molecule. So we can go to molecules. We're going to take this and go to molecules. So we have 1 mole of O2 equals 6.02 times 10 to the 23rd molecules of O2. But we're not done because we don't want molecules of O2. This is a 3-stepper. Let's think about this. 1 molecule of O2. How many atoms in there? So we add on that last conversion, yes. Molecules of O2. In 1 molecule of O2 we have 2 atoms of O. Right? Does that make sense? Does everybody see the logic in that? O2, that equals 2 O's. Okay? Keep in mind that's what we're going to be able to do. So this one is where you see there's an extra step. There's 3 steps. So we cancel the grams with the grams. We cancel the moles with the moles. We cancel the molecules with the molecules, and we end up with atoms of O. How many atoms of O did we have? 78.1 times 6.02. Use your exponent key. Times 2 on the top, divided by 32 on the bottom. What'd you get? 9 what? 3 sig figs?
4.
So this is going to be a 4. Yes, you would round it up. Times 10 to the 24th atoms of O. Be your final answer. So go ahead, you can keep working, try the next 2 on your own. See if you can do those. And I will show you the answers and write it up, and you can check your answers in just a minute. Okay, so let's take a look here. Number of atoms in 0.5 moles of aluminum. Set up a quick little easy T-chart because it's only one step. Since we're going from moles to atoms, the moles diagonal down. Moles of aluminum, there's 1, but there's 6.02 times 10 to the 23rd atoms, okay, of aluminum. When you multiply that, what is your answer going to be? This one, C, yes, it would be 3.01 times 10 to the 23rd atoms. 3 significant figures, yes. Just like this up here. 3 significant figures. Now, up here, doing sulfur atoms, 2 moles of sulfur is just the reverse. It's a one-step one. How quickly we forget the one-steppers. 1.8 times 10 to the 24th atoms sulfur. Then I put the atoms on the bottom this time. So this is going to be the 6.02 times 10 to the 23rd atoms sulfur equals 1 mole. And which one does that end up being? You can't see that. 3 moles, yes, and 2 significant figures, so we would round it to 3.0. That would be correct. All right, so